Okay, so we, chapter 1, we talked about minimizing a loss function, and we, even extended it to gradient descent and minimizing, the loss function for a neural network. In chapter 2, we talked about maximizing a likelihood function as well. And so I thought we could take a tiny bit of a detour, and I'll post some of these notes up. These are just I pulled online on using the optim function that's built into R. R has a built-in optimization function that does a lot of this stuff for us. Okay, so I kind of forced you guys to do gradient descent by hand manually as part of your homework. Okay, and I think there is some teaching value to doing it that way, but in practice, we don't really do that, okay? Yeah, in practice, it's like in elementary school, you learn multiplication and long division, and then in practice, we all use our calculators, right? But we learn things, and so, we have the optim function. The optim function can be used to optimize functions. Optimize in this context, maybe I'll write this. Optimize means to minimize. If we want to maximize, we will optimize the negative of the function, right? Okay. And in any case, you can always just ask RStudio for help. Let me clear out my environment. Just say help on optim, and this is their general purpose optimization function. It's pretty good, okay? And they have a bunch of methods as far as how the optimization function works, okay? The default is the Nelder-Mead algorithm. I know I covered Nelder-Mead in one of my 102A classes, and the other one I did not cover Nelder-Mead algorithm, and I think that's okay. All of these algorithms, you can always go online and just type in Nelder-Mead, and probably the first thing will be Wikipedia, because this is our new source of all knowledge, and there's an explanation of how it works. Okay, the Nelder-Mead algorithm. There's also the Broyden-Fletcher-Goldfarb-Shano algorithm, or BFGS. Everybody wanted their name as part of it. Okay, so we have Nelder-Mead, we have BFGS, we have all these different things. Okay, BFGS is probably the closest analog to gradient descent. So BFGS is very similar to gradient descent, except, BFGS and CG. CG is the conjugate gradient method. This is probably the closest to gradient descent. BFGS is very similar, except it uses basically numeric gradients rather than formulas for this. All of the, I don't know if it matters, these details, but I guess sometimes if one optimization algorithm doesn't work, you can just switch up the method and see if it works that way. Okay? Because in practice, that's kind of a lot of the times what we do. We'll try it one way, and if we get the optimal solution, we're excited about that. If we don't, we just kind of check another method here. Okay? And so to use the optim function, so first we'll just start with unidimensional optimization, and then we can talk about optimizing, multidimensional things and other things, okay? So for unidimensional optimization, we can create some simple function. So here is negative e to the negative x minus 2 squared. This is similar to the way a normal density looks without the kind of the, whatever that constant is that makes the total area equal to 1. Okay, except it's negative, so it goes upside down. Okay, and so this is kind of if we graph it, this is what it will look like. So here in R, I've written a function, and it's a function of x, and I just said, negative exponent of negative x minus 2 squared. Okay. And then I've created a sequence from 0 to 4, and I've plotted it using type L. Okay. Plotted x versus the f of x, and plotted that, and this is what we get. Okay, so maybe I'll run this. Control Shift Enter, I think will run everything in there. So here's my sequence: 401 values, x and f of x. Okay, if we want to optimize this, all we have to do is call optim in the form of optim, and really it just takes 2 arguments, just the initial value. In this case, I can use the initial value of 1, and I give it the function f. Okay? And so, looking at the graph, we can see that the minimum is at x equals 2. Okay? So here, I don't know, if you want to follow along, just all you have to do is just create function f. Here, this is a draft document. I'll upload this onto CCLE, but I will delete it and replace it with kind of a full version later. Okay? Because I was going to add more stuff as the lecture continues. But I'll upload this in case you want to follow along here. Close our poll. Oh shoot, I forgot where I saved this document. Where did I save it? That was the wrong button. B. Oh, here it is. Okay. Sorry. Using optim.rmd. Okay. And so we can see that we'll get our optimal value at x equals 2. If the default method is the Nelder-Mead simplex method. It's not designed to work in one-dimensional problems. So when I run optim 1, f, using 1 as our initial value, okay, what it spits out is 1.9. This says this is my optimal value here, okay? And then it gives you all of this other stuff. If you just want the value it picks for what it is, you can just do $par. $par is going to give you the value that the optimization algorithm has converged to, and it says, it's 1.9. It is sensitive to where your starting value is, and so in this case, I'm starting at 1.9, and it improves to 1.99 right there. Okay, so you just give it some initial values, and it tries to go from there. Okay, we have different methods. One is the Brent method, and again, all of these things you can kind of look up. Brent method for. We'll just do the Brent's method here. Okay, and it's yeah, blah 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 blah. Okay. Okay, and so here with Brent's method, you have to provide it with a lower and upper bound. Okay, so I can just say, between -4 and +4, find the optimal value. Okay, and so I'm just saying, using the initial value of 1, the function is f, method is Brent, give me the optimal value, and it says 2. Okay, which is the correct answer. You can also run the conjugate gradient method. Okay, conjugate gradient, you'd say method is equal to CG, but you have to provide it a second function of f, and that would be the gradient of f. And in this case, the gradient of f for a unidimensional problem is just the derivative of f, right? So if I take the derivative of this function, the resulting function looks like this. Just applying chain rule, you take the derivative of what's on the inside and then multiply it by f of x itself. This is derivative of f, okay? And we can run the conjugate gradient method, just saying optim, my initial value starting at 1, my function is f, my gradient, or in this case my derivative, is df, and the method is cg. Okay, give me back the optimal value. Or if you can ask for everything and it tells you what it did here. Okay. So there you have that, and then lastly you have BFGS. Okay, there's other methods. There's simulated annealing, and then I forget what the LBFGS is, but there's like a modified version of BFGS. So BFGS, it's similar to conjugate gradient, except it doesn't actually ask for the gradient function. It estimates what the gradient is using kind of numeric gradients. So in your homework, you had to do numeric gradients just by kind of like adding a tiny epsilon to your x values and see how that changed the value of the function. With BFGS, they're basically doing that, and they're also doing that with the second derivatives and using that to get it. Okay, and then if we run that, we get optimal value of 2. Okay, and so this is the optim function. The hardest part in using the optim function is just writing your function of f. Okay, function of x. Let me show you. Let's say we had a two-dimensional problem. Okay, and so in our two-dimensional problem, I've got 1 minus x squared plus 100 times y minus x squared quantity squared. Okay, and this is the function that we want to optimize, or in other words, find a minimum of. Okay, and here we have to write. The important thing is that when we write our function, this is a function of x and y. Maybe this is f of x and y. However, when we write our function, we have to write it as a function. You can only have one argument inside your function. Okay? And in this case, our function has two values, an x and a y. So our x here is going to be a vector of, we're going to have an x1 and an x2, and we'll treat x2 as the y. So you can see, 1 minus x, I'm doing x sub 1 squared plus 100 times x sub 2 as a stand-in for our y, x sub 1 squared, quantity squared. So this is going to be our function of f. I could graph that using the perspective function. Okay, so if we wanted to ask about the perspective, you can always ask help for perspective, and it plots perspectives on the xy plane, and you have theta and phi as kind of the angles at which you are looking down on the thing. And so what this requires is, it requires kind of a surface to look at. So here I'm doing, x1, I'm going to go from -2 to 2. x2 is going from -1 to 3. So we have a range of 4, and z is going to be a matrix, of basically this length times this length. So right now it's all zeros. And I'm just repopulating, filling out the matrix just by going through each value of I and j, and every combination. To run our function, I just have run f of, and I'm combining x1 and the x2 terms there together. Okay, so it's a function of just one thing, and it spits that out, puts that into z. So I can run this, and here's my kind of my perspective plot. I can change my angles here if we want to see kind of where this is, how this looks from other angles. So we'll do. So this is where we're looking, and we're trying to see, you know, where our minimum is. Okay, and so the default setting would be, first we provide it an initial value, and in our case, because it's a two-dimensional function, our initial value, we have to provide 2 arguments there. So we've got, so I'm going to say optim 0, 0 of f. This is using the Nelder-Mead, and it returns this. We can ask, you know, what are some of the other values? Other methods, we can say method do BFGS, okay, and we're getting, you know, similar values in our different situations here. Okay, conjugate gradient would require us to supply a gradient term, which I don't feel like figuring out at the moment, but we could do that, and we can also just try different starting values as well to see. But let me see if let me see if what the other method does. Okay. So that's starting at 0, 0. Let me just try at, say, 1.1 and 1.5. Okay. So, you know, depending on where you start, your values might be a little bit different. Okay. But there you have the kind of, you're minimizing what we have for a two-dimensional model there. Okay. In the context of maximum likelihood estimation, we can try to estimate the parameters of a model. Okay, and so in that case, we'd have to write up a likelihood function. And so the you know, let's say we wanted to do kind of a likelihood function for normal data. Okay. Okay, so let's say we'll say, you know, optimize a log likelihood function for normal data. So we can say, you know, so in this case, what we can do is we're going to say our function that we're trying to optimize. So I can just call this, you know, kind of our normal likelihood. This is going to be a function of our parameters, right? So we can store both the mean and what do you call it? Standard deviation in a vector called theta. Okay, and so we will say in this function we'll say our mu will be theta 1, and our standard deviation, our sigma, will be theta 2. Okay, and we can say what we can do is we can just take our data and calculate the probabilities of each of these things, right? So what we want to do is we can, I know I said your functions have to be of one thing, but what you can do is you can also have, you can pass in other arguments, okay? And so the way this is going to work is, so my likelihood function, the first one is the vector that we're going to try to optimize, okay? The theta 1 and the theta 2, which make up our mu and our sigma. But I'm also going to have this argument y. This is going to be our data. And so when I call my optim function, the way I'm going to call my optim function is, I'll have my initial values. I'm going to have the function that I want to optimize, in this case, normal likelihood. I have, whatever else. And you'll notice that in the optim functions, there's this thing that says dot, dot, dot. Okay? Dot, dot, dot means you can pass it additional arguments. Okay? And even though the optim function will not use those arguments, it will then pass those arguments onto, the function inside of it. All right? So because there's a function inside this function, so I can pass, y equal, whoops. I can pass this argument y equal to our data. And now our data is going to get passed into the normal likelihood function here. Okay? And so how can I calculate my normal likelihood? Well, I can just do d norm of each value y with mean mu and standard deviation sigma, right? And I would sum this up. Does that make sense? Oh, if it's log likelihood, I have to do d norm y mu sigma and then log equals true. So for example, I could say, d norm of 0, and it tells me that the probability, the density at that location is this. This would be what I would get if I typed in, if we looked at the normal distribution equation. And if we used this formula for the probability function, right? If I did 1 over 2 sigma, 1 over the square root of 2 pi e to the, in this case, 0, okay? If I did 1 divided by square root of 2 times pi times e to the 0, oops, or just 1. This gives me the same value, right? Because that's what I'm doing. So effectively, that's what I do. And then, if I take the log of this, okay, I would get negative 0.9189135, and I could just say, d norm of 0, mean 0, standard deviation 1, log equals true, and this gives me the same value. So here I'm calculating the log likelihood of our data, and then I'm going to just sum it up. And this is the thing that I want to maximize. So the thing that I want to maximize, I'm going to just do a -1 times this. Okay, because I want to maximize it. So when I run optim, it's always trying to minimize it. So I'm just going to say the thing I want you to return is -1 of this. Okay, and then so we can just kind of test this. All right, so theta I will say is 0 and 1. This is going to be my mu and sigma, and I can say y is going to be the values. Let's say, -1, 0, and 1. Okay. And so I can just say, what's my normal likelihood of theta, comma, y? Okay, and it tells me that the likelihood of all of these three values together is what I have. Okay, and I can just kind of just do a quick check and can say, what's d norm 0, 1? This is what I have. I can say, is turn them into logs, and then when we add these up, we would get this thing. So that's exactly what we're doing. So this is the function that we want to optimize. Okay, and so here I can say we can just generate some random data, right? So we can say r norm. I don't know, how many data points should I do? 500. Okay, And my mean mu will be what? Okay, we'll do a mean of 25 and a standard deviation of 5. Okay. So here now I have 500 data points as part of my whatever we're starting off with. Okay. So now I'm going to run optim, and I need to provide it with some initial parameter estimates. So I can say start off using a guess of the mean is mu0 and standard deviation 1. Okay, the function we want you to optimize is the normal likelihood, and then also pass it in the data, which in our case is just the all of our y values here. So this is maximum likelihood estimation for a normal model here. So I got normal model. Why is that? Optimize, and it's arrived at 24.916 with kind of an estimate of our standard deviation to be 5.32. I guess I can. This is what we have. We can try a different method, see if it gives us anything else. Okay. Oops. It didn't like that. NA is produced. Okay, so BFGS did not work out. Sometimes that happens. Okay. So here's what I have. You know, if I started off, you know, with maybe perhaps more reasonable guesses, okay, you know, we're still getting something a little bit different. Well, something quite close. We can actually see, you know, what is the mean of our y. So that makes sense. The maximum likelihood estimate of our mean, the maximum likelihood estimate of mu is equal to the mean of our data, or something very close to it. And if we ask, you know, what's the standard deviation of y, you know, we're getting something something close to it. I think it's, I already forgot my, is the maximum likelihood of the standard deviation, it's not a unbiased estimator, right? If we want it unbiased, we would have to do the variance, right? So perhaps I should do sigma 2 is going to be the square root of theta 2. Maybe this will give us let's see, something close. Let's see, variance of y, 23.62. I think this is closer. Okay, so there you have using that for maximum likelihood estimation. It can obviously it can be extended to whatever whatever situation that we have. Let me just talk about some of the things that the optim function returns. Okay, so we get $par. These are the maximum likelihood estimates of the parameters that we're estimating. So in this case, my mean is 25 and my variance is estimated to be 24. Okay, as my maximum likelihood. This value, this is the value of the function itself. Okay, so it's trying to minimize the function, and so this is the value of the function that it has minimized. So as you're running kind of the your optim function, you know, when you first start off, if I gave it the values, if I said theta is 0 and 1, I could say, you know, what is the normal likelihood of this at this point? Okay, and so if I have the the function, we can see that the log likelihood is incredibly, in this case, because it's the negative, it's incredibly low, right? So here it's at 162,000, something like that, and it's actually negative 162,000. So that's pretty bad. So what we see, you know, the resulting function that when we found the optimal parameters, this is what it got to. Okay, the counts. This is the number of calls to the log likelihood function that was used. Okay, so in our case, it recalculated the log likelihood function 53 times based on kind of the different things. So it's kind of like how many iterations did it run, and it ran it called the likelihood function 53 times. If we used the conjugate gradient method, which would require us to calculate the gradient of the normal log likelihood, we would have a second function in there, okay, and it would tell us how many times it called the conjugate gradient function to work. Okay, convergence. This is kind of like a status. 0 means it converged to a solution, and it's quite happy. If you see a 1, that means the kind of the max iterations didn't work out. Okay, and so it was unhappy. Messages is if there's any warnings. Okay, we have control. Control allows you to have further control on the optimization function. So let me just zoom in on the help here. Okay, so you can tell it all of these things. Under control, you provide it a list of these arguments, and you can say, you know, I want the maximum number of iterations, okay, to be something like 500, or, you know, I don't want you to run over 10. So I could rerun this optim function here, and one of my arguments could be control, and I would give it a list where I would say max iterations, I can say 10, okay? And so in this case, it's only going to run the thing 10 times, and so after 10 iterations, this is where it stopped, okay? And so we can see, you know, the number of times it called the function is 11, which makes sense because the number of iterations we said is 10, right? So it has its initial call to the function, and it works. And there, you know, our parameter estimates are not that great. You know, we have other values that we can work. We can do the absolute tolerance, okay, and we can kind of shrink it to some kind of value here. So we can say absolute tolerance. You know, we want 1 times e to the negative 4. All right, and let's see. I'm a little nervous. Okay, maybe 6. It's still converging at right around the same value, I guess. That's what we have there. Okay, so you have a set of controls there as far as the fine details of how the optim function works. Let me see. I guess that's, I don't know if there are any questions. I just wanted to demonstrate the use of the optimization function. If, I think in even for the neural network, I have a case where in one of the sample codes I've used optim as a way to optimize the weight matrices. I think for the handwriting recognition. It just required that I have to rewrite the function that we're using as a function of the of one vector. And so if you wanted to use optim, which this was not part of your homework, but in your homework, you know, you have 19 parameters to estimate, right? So you have your 2 weight matrices and your 2 bias vectors or bias matrices, and so, you know, there's a total of 19 things. You have to put all 19 into one function, one vector here, and then you would split those out. You'd say, you know, the first 6 first 8 form weight matrix 1, and the next 3 form, you know, the or however many, you know, form your bias matrix and whatnot. Okay, well, I guess we'll end a little bit early today as far as the usage of the optim function. Let me I'll add a little bit more to this this notebook, and I'll post the notebook online, and you can kind of use that as a reference for how to use the optim function. But it's very versatile as far as both the ability to minimize and maximize your functions. Okay, we'll see you guys on Wednesday.